Okay, we'll go ahead and start. Ken, do you want to take the floor?
Hi. Let's see. So over the last week, we've been trying to get the ZC706 card programmed with proper clock frequencies and set up the JESD interface. I think we've made some progress. There's a couple tools that help us. There's one, it's called a wizard. Let's see, it's the Talese configuration wizard, and then there's also the TES software suite itself that helps you basically set up profiles. There's a lot of different restrictions when you choose different clocks and stuff with these platforms. So trying to find one that works, and then how to actually program it. It seems like we've got a way to directly connect now to the. You can directly connect the TES to the to the board and evaluate things kind of in real time, and then it spits out a config script. We're still researching how to incorporate that script, but that script is ordered to set a C configurations that you run to configure the card. So how to incorporate that in the build correctly, TBD. But at least we've got the like a valid configuration. It programs successfully. There is some additional constraints that the wizard doesn't know about that have to do with the lane setup. So given we're trying to emulate like a 20 megahertz channel. What we've seen is that there's a lot of different restrictions on the sample rates and stuff with the with this FPGA, and I think we've got a combination. It's kind of a little bit off the beaten path because I think the typical LTE transceivers like to use like a built-in block of 30.72 mega samples per second. We're having to bump it up just because I guess this radio is designed really for higher bandwidth applications typically than what we're trying to use here. So we're kind of digging out at the bottom end of it. But it looks like we have a config that can at least program, and we resolved this JESD issue. Basically, it was a mismatch. It requires the same speed on the JESD observe, receive, and receive Certus lanes. So we solved that by widening up the observe port. So the observe RX has the same sample rate as the transmit, and it's half that of or it's twice that of the receive itself. But now the actual lane timings are the same between RX and observe RX for by doubling the lanes on the observe. So I guess that's the latest, and we'll just continue to inspect how do we actually use this to run the radio. I think that's the next goal. But I'll turn it back to Michelle.
All right, thank you so much. That there was lots of learning and good steps forward over the past week, and it's really nice to have a profile that loads. The next step is to actually take this profile, go back to the target, swap out the Petalinux build with the hardware in it, and then show it actually taking, because we've programmed it from the transceiver evaluation software with the modifications. Now take that profile, go and see if there's any mismatch, and I suspect that we'll have to modify the JESD lane configurations before that will work, but that will be another thing to figure out, and then we'll put that into the documentation. At first, it looked like that because we were changing clocks that we were going to have to do that entire VCXO, change it from HDL all the way through. But no, we're actually not changing the VCXO. We're configuring the clocks with the onboard dividers and all that. So Yeah, so plenty coming up in the next couple of days. Maybe we'll get some progress today. I have some time, so I can help you, Ken. So thank you. It's a kind of interstitial work to try to get these things configured and to make it possible. Now you did mention that you may have to go back and modify the polyphase filter. Have you been able to figure out if that needs to be updated?
Um, yeah, that has to do with the internal kind of the system clock. So there's a sample clock, and the design that I've put together in the wrapper with the polyphase, it assumes that they're asynchronous, and there is a synchronizer involved, which, if I recall, it's like it requires the system clock to be at least twice the sample clock to kind of synchronization of the basically the enable. As the samples come in, they're registered with a strobe, and that has to kind of propagate through the synchronization. So the synchronizer is kind of a simple step across handshake. And so we have to decide, it may be simpler to just assume that we can set, now that we've kind of dialed in a sample clock frequency, we might consider just going with a truly synchronous interface to the sample clock. That would allow you to run that interface at actually a lower system clock if it's a sample clock, like it could be 80 megahertz or something. Right now, it looks like we might have to run it at maybe 120 megahertz or something. So we'll have to. I'm going to go back and study that synchronizer circuit just to see if it's 2 clocks or 3 clocks that it breaks, or that it requires. Um, but yeah, as it stands, the design is basically assuming that the device clock is some higher clock than the sample clock, and that's kind of an open study right now. Yeah.
Okay. Well, it sounds like you have the question well in hand, and hopefully we'll get the answers understood and then documented. So thank you. Some big steps forward. All right. And Matthew, you have the floor.
All right, good morning. Um, some news and progress on the Pluto MSK. Um, so both Everest and I have clean builds and been able to build the firmware and load it onto our respective Pluto devices. Um, we weren't able to get there, so I set the base the 0 configuration status register just to a static value so that we can know that we're actually reading back from the configuration registers correctly. And that wasn't working, but Everest had posted in the Slack channel this morning that he got it to work. He changed the address location and then used the devmem command on the Pluto and was able to read back the AAA 5555 value from register 0. So that's exciting. So now we just need to see if we can, maybe at some point get it to pass some data. So we have a path for clean builds, and at least are interacting with, looks like we're interacting with the configuration registers. He didn't give details exactly where he changed it, so he's not accessing, I don't think, through IIO, but rather through a memory mapped location within the Linux kernel. So I'll ask him for some more details on that. But at least, we're getting, there's some evidence that it's alive.
Okay. I saw the conversation from yesterday, and so I have a little bit of what I think uh, might be going on. And this is from the DVBS2 encoder, where there's a block that has a register map, and that this is the AXI sort of access for that.
Mhm.
And then there's there's like a memory map in the documentation for that block. And so whenever, like it was 2 weeks ago, right before Remote Lab had issues, that every user was like, well, you know, the things that the DVB-S2 encoder is doing, that's what he kind of expected to see. So I suspect that maybe this is what he was able to change to find the actual address. And my question, the reason why I kind of took these screenshots and brought it here is like, is there something that we needed to add to the HDL in order to kind of achieve the same sort of thing? And then maybe we need to like put in a little table or something like that. So that I guess that's my question. But it sounds like that you've already raced past this point and that it's working.
Yeah, I think what the stuff you were just showing, I think that's what he did, in that he changed the base address for the configuration registers to a fourth. I'm just looking where it is in Slack. It disappeared, but to a 4.3. Oh yeah, 4.3 C0000. So that he changed the base address to a similar address range to what you had just shown and on your screen share. And so I think in doing that, he was now able to read back that register. So it seems like what he did is along the lines of what you just showed.
Okay, cool. Yeah, I have enough. I remember doing this with the encoder, and then there is a pretty nice shell script that we have that we set up because there's a lot of registers to look at on the encoder to figure out if it was working correctly. But we do have a shell script that allows you to access the registers, which is just kind of nice. So if you just want to run your hardware, then you can sort of run the shell script, and it puts it on the screen for you. And then I remember doing the memory mapping from the code for application. So I'll do my best to catch up and see if I can't duplicate the clean build. And it's really super exciting, actually. So there was some additional things about timing. So there was still some timing issues, or are
Well,
those?
there was I added to the XDC file a couple of constraints, since there is a asynchronous clock domain crossing. I think those constraints, when I was looking through the log files, didn't take, but I was still getting a clean build. The biggest issue, there was an error in the VHDL. I forgot my clock tick event on the one process, and so it was just clock equals 1. So it just made register or latches instead of registers, and the latches just, they're transparent in one state, so it was timing from the register all the way through the address decode through the latch and back through the address decode to the read back to another register. So it was this incredibly long path that was failing. But once I was able to see the timer import and saw that they were latches, I knew what was wrong and fixed it. And so I think that was the main thing that was causing the problem. And so that with that fixed, yeah, everything's timing clean, and I think we're like 77% utilization, if I remember the utilization report. So we're, you don't typically want to go much above that, but I've worked on designs where we were at 80+ utilization and still got things to work. But yeah, 60 to 70 is probably a good target.
Wow. Okay, but that's with the transceiver on the Pluto.
Yes.
So not limiting it to just a transmitter. I think that's really good news. That's fantastic.
Yeah, I didn't spend a lot of time looking at the reports. I mean, I was expecting that, if it uses the DSP slices, where we need to, and there's actually not a lot of multiplies. Most of the multiplies turned into like multiplexers, because it's like multiplying by plus minus 1, so I'm just either, just taking the regular value or the two's complement in through a multiplexer. So, and then I didn't look at the sine cosine lookup tables went into BRAMs. I was hoping or expecting they would, because then that obviously would give us, we wouldn't be taking up a lot of resources with the lookup tables. So I want to spend a little more time looking at the logs and the resource utilization and make sure that, you know, that everything makes sense. Because, you know, there might be room for optimization if it didn't make the correct choices.
Yeah, this is substantially better than the Simulink to HDL coder to VHDL to path, which just a real, not even a full transceiver completely blew the budget and could not be fit on the Pluto as a target. So this is just from that metric alone, or from that comparison alone, it's good to have a model in Simulink, you know, but
Yeah.
the path of using HDL coder is can be difficult. And there's lots and lots of things that probably could be done along the way. So
Yeah, I
you
mean
know,
that's always kind of my view. I mean, it's a double-edged sword. You get some early on advantage, right, during initial design and prototyping, but then sometimes you lose that knowledge of the FPGA that, you know, an RTL designer would write code in a certain way that, you know, is going to, you know, already be somewhat optimal for the FPGA versus something like HDL coder wouldn't have necessarily. I'm sure it gets smarter over time. They get better over time, and maybe they even add AI or something to it, and it'll do as good as a seasoned designer. But I don't think we're there yet.
no, and you know, you have a hammer and you have a screwdriver, and they do different things. So, and if you try to use one for the other, you get this. So, yeah, this is fantastic. Okay, so yeah, well, we have plenty to
So
do over the next week.
kind of one other question. I mean, I was looking at the Pluto FM and the OPV mod that is already there that we have already implemented. So I guess my question though is, so yeah, we're able to read and write the registers through DevMem, but I'm not, is that really, do we want an IIO backend for accessing these AXI registers in, you know, so that, you know, we can run an application, say remotely, and use IIO to like assert the PTT and you know, set up the DMA and everything, or yeah. So I guess that's what I'm just wondering is if we still want to pursue being able to access the registers via IIO. I kind of makes sense to me that we would, but I just you guys have been doing this longer, so I'm just curious if we have any other viewpoints on that.
Yeah, that's a really good question. I'll let Paul speak to that. See if he has any opinions. The way that I have used this hardware before is pretty straightforward, and that's to memory map things and then write the code, write the C code, and at the application layer. But I think Paul may have some other information on this.
Well, not so much information as opinions. Um, the um, the code that I had to create to make Pluto TXFM work, controlling registers that way through IIO, was kind of horrific. IIO is not designed for controlling random stuff from registers. It can be forced to do that by pretending they're voltages or whatever, and using that sort of IO. So on the one hand, I think it's a great idea to enable it through IIO because it's consistent with how the Pluto has been implemented and how you'd have to do it if you were going to use an IIO application to program it exclusively. On the other hand, I think it's ugly and horrible, and I am not happy with having that being the primary control interface. So I think it's a hard call. I don't know how much work it would be involved in implementing that IIO part of it. I do know that would end up being in the kernel, and that would probably be an ongoing configuration nightmare for people trying to run this code along with other IO applications on mixed with other computers. So that's what I have to say about that. That's not a definitive answer, I know.
I think that's a good perspective. I was digging through the IIO drivers in the Linux, in the Pluto firmware folder yesterday, and I mean, yeah, there's nothing intuitive about it. They're not, they're maintained as part of the kernel, it looks like, versus but I don't know that they're up, that they're in the upstream kernel, and may just be in this local build for Pluto. But it looked like potentially we'd have to write another device driver that would sit in the kernel that would interact with IIO and, expose all those interfaces that are exposed for like the ADC and other pieces. There's one there, and a driver for the TDD, which is all in the FPGA. So that might be a good template. But I wasn't able to, wasn't able to make sense of it yet. I just would have to spend more time on it. So I mean, yeah, I like the consistency and the abstraction, right? Because it allows you to run your application. It doesn't have to run on the Pluto then. It could run on a host PC.
Yeah, from anywhere.
But if you're using the DevMem, I think it would have to run from the Pluto, or you'd have to have another separate network socket, right? That would allow you to, read and write the memory mapped location separately from the IIO data stream.
Yeah, that's my understanding. That's all I've accomplished with this hardware is that type of programming, and all local. Was a application running on, right there, running on the target. So yeah, you're right.
So yeah, I mean, it's not a great call. I mean, it's
It's
like,
hard.
both would work, but both are not ideal. So it's unfortunate that there's not a better, just, the AXI can't just be in /dev, for example. That there was an AXI, a character-based AXI interface in /dev would be, I mean, it still requires you to run locally, but at least it would be consistent and not something necessarily that, you'd have to write drivers for every little thing you put in the FPGA. You just have a generic AXI driver for, it's, I think, mainly applicable to Zinc that would allow you to read and write any AXI address space.
Is there possibly maybe a third way? Like I know that there was a way to go through like a web interface, a pretty simple one. I learned this from the Linux class, where you could talk to GPIOs through HTML interface. Is there any way to use like HTML5 or something like that to do this, to do a like remote, and then it'd be hosted on the target? Like I was able to turn off and on LEDs, and
Yeah,
that's
there's probably a way you could do that. If you had, if it was like a web-based app that was running on the target that could then read and write the memory map locations.
That would be suitable if you needed human control, but what you really need here is a way to control it from inside a program. So something a little more raw rather than HTML would probably be more appropriate. And if you needed an HTML front end to it, you could write one.
But I mean, if you did do it as a web app, you could make it like an API so that a program could make API calls over the HTTP socket to set and read and write values. So I mean, I think it could be done that way. Again, I don't know that it's ideal, but it could. But I mean, you can even extend that then, for example, and make an RTC or WebSocket type interface and run audio over that. And then, you could have a encoder decoder running on the target that then put the data into the buffers you know, so that could be interesting is, you know, using like WebSockets or RTC for real-time data, and then just some API calls for configuration and status.
It sounds like we can't really go wrong if we keep, like, if we just make the memory map local, you know, application, for lack of a better word, that work in the short term. And it sounds like we have a couple of options to make it more useful and more abstract.
Yeah, yeah. I mean, it's probably the easier way to go than the IIO. So and it might be applicable across different targets, where maybe IIO, if you wrote a driver, might be very specific to Zinc targets.
Oh, yeah, that's a good point. I'm so used to thinking zinc only, but that's a very good point. A lot of the decisions that we're starting to make, you know, if we if we reflexively just address zinc, end up boxing us into the zinc world only. So I've gotten accustomed to thinking just in terms of zinc, but that's a really good point.
I don't follow it out. How does it tie you to zinc?
Well, I mean, it's just like if you wrote an IIO driver for like the MSK read and write, you know, registers, that would be likely, you know, somewhat tied to zinc because it has the ARM core internal and then access to the EXI. So say if you were had say a SOM on the board, like in the proposal I was making, if you had a SOM that was running your Linux code, and then the FPGA was external and separate, and over, say, you were accessing, say, via SPI, then that IIO interface wouldn't be useful anymore, and you'd have to then, you know, do a different layer and change your application to talk to the different interface, right?
Yeah, you'd have to kind of either that or like back up and have a parallel. The driver implementations would be different.
Right.
At some
Right.
point, you
Yeah. So
cross
you might,
over into it being specific to that target, like a Snapdragon or whatever.
yeah. Or I mean, say you put a soft core in an FPGA instead of the ARM. I mean,
Yeah.
then again, you know, it would, things would change, and then you'd have to, you know, do a whole bunch of different stuff. Where in maybe I'm just thinking IIO is very low level and specific, and you know, you'd have to redo that for every new target. Whereas if you say like SPI is pretty common, so you know, if we're using SPI, I'm not saying we can or are here, but then that is more portable, is what I'm trying to suggest. Or at least if on the target the Linux stack had a more, like if it was memory mapped all the time, then any target can be memory mapped potentially, and so whatever server code you were running there to accept commands and then update the FPGA configuration, it would all be through memory map, and not, you would need the IIO driver, and then hopefully that memory map approach would be portable across targets. Whether or not it is, I don't know, but I guess my only thought is just thinking that the IIO approach could be very specific to the Zinc. You could take that same driver and port it to another target, and maybe it wouldn't be that difficult. I'm just kind of trying to stay out of the Linux kernel as much as possible.
Yeah, it's not a bad.
Well,
I mean, it might be the best approach. I don't know.
I know, but it's good
just,
instincts, I think, to, you know,
yeah.
we want to minimize the amount of things that we have to go and touch, because anytime you touch or modify, then that modify means maintain, and you know, we're already, I mean, just over the past week, we've already looked at like, you know, so we're already doing all the stuff to set up Linux. We already have this flow. We already have like device trees and all of that, and then, you know, anything additional that we put in there. So you have to be kind of cautious. So I think that's a good instinct to kind of limit the amount of meddling that we do with the kernel.
Yeah.
So I think memory map for now, and we'll keep it simple, and and I think that getting that working over the air, once we get like a firm foundation there, then these more abstractions or making it more sophisticated will be much easier to talk about, and it'll pay off.
Yeah, I think we're in danger here of mixing up two different interfaces. The memory map and SPI would be at a lower level, and IO is on top of that. So if we wanted to have the flexibility that IO gives us, namely where the same application could run on a local, even inside the Zinc, or on a SOM, or on a remote system on the other end of an Ethernet, or on the other end of the planet with internet, performance permitting, then we have to use IO. That's how you get there from here. If you want to have that kind of flexibility, it doesn't really matter whether you're using SPI or memory mapped IO. You still have to have a local processor that's processing the API that you're presenting to less local processors. And we could invent a new way to do that. And it would be prettier and more applicable to, more intuitive for what we're doing. Or we could just use IO and swallow the ugliness.
Yeah, I mean, I think I think this is a good discussion. I always find in engineering, working through and arguing these different points, obviously sometimes it's very adversarial, but it's in the end, it's more like polishing a stone or something, in that, we're taking off the rough edges and figuring out, like, collectively, from all our experience, what's the best approach. And so, I mean, I don't know what it is, and IIO might be it, but and unfortunately, this is just part of the pain of engineering, is we'll have to kind of go down some roads, and we might find they're not the best roads, and then we'll have to try some others, and that's just nature of the beast, I think. But yeah, I mean, I don't want to exclude IIO. I just I want to find what is going to be suitable and like Michelle said, maintainable, because that's always there's so many things we're using already, like even the code generator for the channelizer, we had to muck with that to get it to work. So I mean, things aren't maintained, and so that we've seen the problems that causes already. So I mean, I'm sure we'll find a good approach. So
Yeah, I'm optimistic about that. I think that we can absolutely pick a quality solution. So I think that I'm very much looking forward to achieving what you and Everest have achieved over the past couple of days, and catch up and get it working, and then kind of move forward to test it over the air with data. I think that's going to be super exciting. To me, that's the best part, is to where it starts to work over the air. And I don't think we're too far. So
yeah, I'm looking forward to it. I'll need to step away now, but
okay.
Appreciate it.
All right. See you soon.
All right.
Then, Paul, did you have any updates about hardware additions to the Unraid server for Remote Lab?
I can say a little bit about that. First of all, the replacement SSD that we dropped in for the failed one seems to be working. I'm not sure where all those 30 megabytes of corrupted data went, but I'm happy that they're not in our way at the moment. Still a possibility of running into that. On the performance improvement side, I have hardware in order now. I have in hand the card that will give us 4 new NVMe slots. I had to pick that up used because it's a little bit obsolete in terms of working with this particular motherboard. It chose to use one that actually is recommended by the manufacturer of the motherboard, so as to avoid any compatibility problems. And then the drives to fill it up with are on order and should arrive tomorrow, I think. And then we'll have to experiment with a couple of different configurations until we figure out how to get the most out of it. But there's every chance that the VMs will be somewhat faster, maybe a lot faster, when we're done with this experiment, and we'll have more storage space on every VM. and other improvements in life.
Awesome. Thank you. All right. Any other news from the remote lab?
There is a new version of Unraid. I was mistaken when I told you the other day that it was out. It's actually just released in beta. So it'll actually probably be a few more months before version 7 of Unraid becomes released. I don't think we want to mess with betas. But it does have some improvements that'll help us manage the VMs, including snapshots built in and some other capabilities. So that looks encouraging. I need to learn more about it, but I have plenty of time because they're still going to be doing beta testing for a while.
Well, that's big news. Okay. Looking forward to that. Greetings to Jeremy. I think Jeremy's been looking into some performance testing of the Costas loop. So Jeremy, if you want to take the floor and tell us about that or anything else that's been going on, and then anything you have planned, any resources you need, or any roadblocks that you have.
Yeah, okay. Can you hear me all right?
Yes, you sound great.
Yeah, okay, good. Okay, so last week I managed to set up access to the remote lab with the help of Paul, I think. I haven't tried WireGuard out yet, but I've been secure shelling around and able to get access to ChocoCat and that kind of thing, and been reading my way back through the Slack channel to try and figure out what's been going on with Opulent Voice. Found some papers on costless loop costless loop analysis, and been working through the mathematics of some of the review papers, tutorial papers, where I think I found a typo in one of the papers actually. So that's the level of detail I'm trying to go into. But my understanding is that the kinds of modifications that have been put in place for MSK demod make it a non-standard costless loop, and actually there are some tweaks that need to be incorporated in to the analysis, which I'm not totally clear on. I've come across the repo, managed to build the CocoaDB test benches and run the simulations, and getting familiar with the HDL. I've checked out the C++ version of the OPV demod and modulator and had a little play with that. Yeah, and I started with the intention of eventually simulating, given that assuming I can get to the point where I can come up with some parameters for the loop filter. Checking that by simulation is obviously a good step, and so I've been playing around with isolating the Costas loop, the RTL implementation of the Costas loop, and modified the build slightly. I'm trying to unpick it all from I guess the top level MSK HDL. I'm trying to work out using the diagrams in the documentation directory, trying to figure out exactly what signals are doing so that I can drive them from the CocoaDB layer. So I'm kind of in very early stages of a lot of these things, so I'm going to need a bit of hand holding, I think, at some point or other for doing some of these activities. And certainly haven't come across these. I presume the AXI buses. I haven't had first-hand contact with these kind of things, and some walking through of the diagrams might be of help to me at some point. I don't know who's best to try and do that with. But that's about where I am. I'll leave it there. Any comments or advice would be most welcome. I think the person that's just dropped off the call, I think he said he's working on some of the mathematical development as well. So I'm a bit wary of duplication of effort, but obviously he knows what he's doing and I don't. So I don't know where to focus my efforts best. Maybe it is to continue along trying to get a simulatable isolated Costas loop or modified Costas loop. Anyway, I'll leave it there, and perhaps Michelle, you've got some comments or advice.
Oh, sure. I think that you're doing exactly what is needed. So the things that we're doing, there's a lot going on, and there's a lot of moving parts, and it's in development. So I think your instincts are really good. The goal to like, okay, here is a design with a test bench. Can I get that test bench running? Can I simulate? Can I see what's going on? Can I start to change things? Can I change the inputs and see the outputs change? Is exactly the right path. And then yeah, kind of like isolating the Costas loop and making sure that you can, actuate it, and then sense the output is precisely what you'll need in order to do the task of, hey, let's look at the Costas loop and make sure it's functional, stable, and so yeah, you're right on target. It's totally okay to be kind of confused and overwhelmed. Yeah, this is MSK is really quite interesting, and it took both Matthew and me and everybody else that's looked at it multiple rounds of sitting down and puzzling it out and looking at the math and the block diagrams. The block diagram for MSK transceiver from the papers that we've been looking at, which they should all be somewhere back in the Slack, traded back and forth, and I've tried to put as many of them as possible in the documents repository. Some of those diagrams are very, very terse. Like I had trouble interpreting the symbols, digital signal processing symbols in some of these diagrams. And then recently, so my implementation that was in Simulink, it turns out that I had the two different clocks reversed. So this is just, and then that things like this will happen. So yeah, Matthew's a really good person to talk to about the diagrams. We use draw.io for the diagrams. So and the original, like the source document, you can import into draw.io. So if you go look at those documents in the MSK repository, you should see the draw.io diagrams. So those are editable. The PNGs are the output from that. So if it comes to where you go, oh yeah, okay, I get it, and you see that you can improve the diagrams, I think I still have some marked up diagrams where I've put all of the signal names onto them, and then so that I could understand and walk through it myself. So I actually owe an update to the repo. And then just another heads up, very soon, hopefully this week, we're going to move the MSK repository that's on ChocoCat to GitHub. So we're going to go ahead and surface it up to GitHub, since things are coming together and we're starting to get results. And this will also give us some diversity in where the code is. So as we nearly learned a kind of a hard lesson with with remote lab SSD failing, that maybe get, if it's on GitHub, then we're in good shape. And the vast majority of our work is, so the MSK is just about ready to go move to GitHub. But what I'll do in between me and Matthew, we'll make this very clear, where the repo is, and start filling in more documentation for it. So it sounds like you're doing exactly the right things, and your instincts are good, and getting a really good handle on the Costas loop and making sure that it is doing what it's supposed to be doing is very important. So it's deeply appreciated, and I just have lots of optimism that you'll be able to achieve this, and probably sooner than you think. So yeah, just ask any questions that you have on Slack, and you know there isn't any dumb questions. This is complicated stuff. So if there's something that you're confused about or can't find, just ask. We're here to help.
Yeah, will do. I guess being kind to oneself is good policy, and
Yes, that's right.
yeah, yeah. It's going to take me a little while to get up to speed, but I'm glad to hear that you think I'm along at least partially the right track. Okay, thanks.
No, you bet. You absolutely are. All right, and then let's see. I have a little bit of a report. What I've spent some time on over the past week that I'm hoping to move to FPGA target at some point is it's a AI/ML, artificial intelligence machine learning project to design a model that will demodulate decode RTTY, radio teletype, and that is a sort of a warm-up project just to learn how to do it and to get through all of the learning curve, and to tackle Ribbit, a more sophisticated digital protocol, and see if there's any way that can be done. It's coming along. So over in the AI channel is some images from the training, validation, and test of a model with synthesized RTTY messages. And after figuring out the ratio between training and validation, after figuring out what that ratio means, in other words, allow it to train and then attempt to validate, because validation is a subset of your entire data set that you're using ever so often to kind of get a handle on whether or not the training is working. And so if you do not have that ratio of set correctly, then you will harshly limit your training ability. So that was what I learned over the past week, and the before and after from changing that ratio can be seen. And then you can sort of see what's called a confusion chart. And one axis of your table, big grid, is the actual thing that you're attempting to classify, and then on the other axis is what it guessed. So you have truth on one axis and the guess on the other. And what you should see is a very strong diagonal, that for this value that you have the truth, then, this value, your guess should match. So you should see a strong diagonal line, and you can see the emergence of a fairly strong diagonal line. The accuracy of the RTTY model is only in the 80% zone, so it needs to be a lot better. We would like it to get things right, even in noise, even with the existence of noise. So that's where that's at. It's coming along. This is all still in MATLAB, so it's not yet to the point where there's any code written or anything like that for an FPGA. But that work is I'd like to move it to something like the Pluto in the near future. So I doubt that's going to happen over the next week. But if you're interested in that sort of work and you want to see the documentation so far, there's a PDF of the MATLAB live script over there. And if anybody sees anything that could improve that project, or pointers, or hey, have you thought about this? Or hey, I know why your upside is capped on the training. Then please feel free to comment and critique. It's always welcome. All right, that's it for the week. Any other last comments or questions before we close?
Yeah, I've got a quick question. Where does the Simulink MSK model live?
Oh, that is.
I guess that if you could answer it in Slack, I'll pick it up from there. Yeah.
Yeah, sure. Yeah, I'll make sure that that's known, and I'll make sure that should be it should be something you can check out on GitHub, and I'll make sure that that's the case. But it would be on Karapi. So we have ChocoCat, which is connected to the ZC706. Karapi is attached to the ZCU 102, and Karapi is the one with the MATLAB and Simulink license. So a lot of the MATLAB and Simulink work lives over on Karapi. All right, and I'll see you all on Slack. Thanks so much. Your time and attention is deeply appreciated, and could not do ambitious things without you. So see you next week, and see you on Slack.